list. Okay, we're up to 29 participants. I will start this show now. We can continue, teachers will continue to monitor the waiting room so that people who show up late will be admitted if they log in with their first and last names. So I think you can see my screen here. Preview of online lesson 5.2 is the first thing on my agenda. This has been pushed out to your Google Drive, so you should have a copy of this, online lesson 5.2, available for you to work on. The first page is the review of the week. We're already on Thursday. So as it says, Thursday, students should start online lesson 5.2, dimensional analysis part 2 with the due date of Saturday. Although it does not say so on here, we also have Alan. Alan is giving his presentation on FIRST Robotics, which is awesome. Woo! Is it all capitals? Maybe it is. I'll capitalize it. So it looks important. It is important. And then tomorrow I'll be doing an update on the disease that's making us all stay home. I started doing some serious research on that this morning, and I learned a lot already. So I'll be happy to share what I've learned with you tomorrow. So this is what you actually need to worry about. I hope it's not worrisome. This is video instruction from Ms. Holtz this time. It will teach you how to do dimensional analysis for chemistry. Dimensional analysis is something you're supposed to know how to do when you go to college. And this is the way we're hoping you will learn it. And these are nice fillable boxes, as you can see. You can do this all on the computer if you like. You can print it if you like. And we're trying to use more color. As you can see, there's color here, which we couldn't do when we printed it on paper, but we can do when it's online. So take advantage of the color. And there is no, you can see there's no pre-test for this one. You've already done the pre-test for the week, but there is a post-test. And that post-test will be at the end of the assignment. To this one, we added a challenge question at the end. So I'm hoping those of you who are honors types, high flyers, A students will have fun with this challenge question. But again, you can see we're using the pictures and the colors. And it tells you can do this in 3 steps, boom, boom, boom. You could also try to figure out a way to do it in 2. And there's the link at the end to post-test part 2, which is the Google form that you're all familiar with. So that's assignment 5.2, which is due Saturday. Says so at the top. Due date, Saturday at midnight. Let me show you briefly. Our data from part 1 was very good. So we're up to 220 responses for the pre-test for lesson 5 with not a bell curve this time, but it's certainly spread out. And the post-test for part 1, which was due on Wednesday, but you could still do it today. If you haven't done it yet, do it today. We're at 215 responses, and that's a very good sign there that the vast majority are earning 5 out of 5 on the post-test. So there's one more post-test for the week. And you'll be able to do that when you get to it, after you've done the instruction. Boom. I'll pause here, see if there are any questions. You can raise your hand if you have a question, or you can type your question into the text chat and it will get to me that way. All right, you'll have another chance to ask questions in the breakout rooms, which is less intimidating than asking your question in front of everybody. But I'm not seeing any questions at this time, so let's turn it over to Alan. He's going to talk about FIRST Robotics. I put a picture here. This is from, Google told me it's from 2019 competition. And maybe Alan knows what that was. But he's going to talk about his current competition and the robot he's built. And I think, let me briefly talk about 4 before I turn it over to Alan. That makes a better sequence. So there's 4. You can see tomorrow, Friday, I'll be talking about the virus, and this on screen is an example of the kind of thing I'll be discussing, which is testing. How do you test? How do you know if you have this virus? Besides symptoms, saying I feel sick, what does science do to say, yes, you do have this virus, and no, you feel bad, but it's not because of this virus, it's something else. So that'll be what I'm talking about tomorrow. And we should have time, I think, to do a breakout room today, which is Thursday. So now I will get out of the way and let Alan share his screen and talk about FIRST.
Hi guys, I'm Alan, if you don't know me, and this is my presentation on robotics. So background, FRC. So FRC is an international robotic competition that occurs each year, and there's 4,000 teams around the world. And each of these teams have about 30 members, and they each build a robot to compete. So each year there's a 12-week build season where robotics teams around the world build robots based off of new games that are released every year. So each year there's a new set of rules we need to design a robot around. And in these 12 weeks, so they start around in January and around April. So it'd be usually it's a really big season, or like most accumulate hundreds of hours. And the first 6 weeks are spent on designing, manufacturing, and programming a robot. And then the second 6 weeks are filled with regional missions. So this is kind of called build season, and then the second 6 called competition season. And then there are regional competitions that will qualify a team for international championship. So this year's game was 2 hours and 30 minutes and 30 seconds long. And the first 15 seconds are dedicated to an autonomous period, where robots need to move around without human interaction. So what we have human drivers that pilot the robots around. The first 15 seconds, the robots move around with pre-programmed code or using sensors or like a camera. So each match, there are 6 robots total, 2 alliances. So the alliance has 3 robots that work together to score the most amount of points. And there's 2 alliances. So each robots, they try and outscore each other. Whoever scores the most points wins the match. This year, our task was to intake and shoot 7-inch diameter balls, these yellow balls, to different goals. So there are 3 goals or ports. So the bottom port is this low door, gives you 1 point per ball, and then the outer port, which is this hexagon right here, this outer hexagon, scores you 2 points per ball, and then the inner port, which is that tiny circle in there, scores you 3 points per ball. So the small circle, the inner port, is obviously the hardest because it's really small. And you have to be really accurate to get it. And in addition, the last 30 seconds of each match, robots can lift themselves up to earn 25 points. So I'm not sure you can see it, but there's kind of a climbing rung here, and the robots need to extend up and be able to climb. But another problem is that this climbing rung actually swings. So you can see it can swing here, or it can be flat. So it's a little bit harder now that I can see. So my robotics team called Code Orange 3476. which is you just get assigned team numbers, so there's no like, and we know which teams are wins. So it has a 10-year history, but I've only been on the team for 3 years. And we are a team based out of our sponsor graphics workshop in Irvine. And then our 30 members, and we're divided into 5 sub-teams, which is design, so design the robot, and then electrical, which wires up the robots, and then programming, which programs like the auto and also like vision tracking. I can get later. And manufacturing, which makes because we make all of our parts, most of our parts custom in our workshop. And this is the robot we designed this year. So I'll get into that later, but so our design process. So we use the same process every year to make sure that we come up with the best ideas. So whenever a new game is released, as a team, we sit and we read over the rules very carefully. So the rules they actually come in like 100, 200 page manual that we read out loud for like 3 hours, which is boring, but it makes sure that we know the rules really well. And then we function our robot and rank them as wish, prefer, command. So like command, for example, would be like ground, but a wish would be like we want to fly. Like that would be helpful, but it would be extremely hard to make. So once we figure out what our robot wants to do, we do prototyping. So we build basic designs out of first cheap material like wood and test them. So this is one of our prototypes, which is intaking balls.
Yeah, do it.
So what we're trying to do is trying to move them and like serialize them. So we're trying to seal them out.
Yeah, do it.
So we're trying to
yeah, do it.
These balls so this prototype right here, it's kind of made out of wood, and like this is a robot, but it's made out of wood, so it's cheap and we don't have to spend that much money on it. So through prototyping, we get an idea what the best design will be, so we will pursue it. And then after that, the CAD sub-team will begin to design a detailed model of the prototype. So I lead the sub. I'm CAD lead, so my job is to assign all the CADers their roles and also ensure that each of the designs don't click inside each other. So like maybe someone will build a climber right here. So this is our climber, and I need to make sure that it doesn't interfere with. So we use SolidWorks, which is kind of like Fusion 360. It's a 3D modeling program. So we design it in 3D first. So this way we can put the robots together in CAD first and then use the model as kind of like instructions. How Legos have instructions, use the CAD model as the instructions. So this is our CAD model, and I actually have it right here. So you can like rotate it around, you can see each individual part. And then, so after that, it turns into the real robot. So it's what it looks like in real life. So we're trying to make it as identical as possible, but you can see there's a bunch of wires everywhere because we didn't CAD those in. So I designed the hopper this year, which is this mechanism. So this is what it looked like in the prototype. It didn't look great, but we would want to build it better. And then this is what it looked like now. So what the hopper does is it takes the balls and it has these two like fin kind of brushes. These two, and so these brushes kind of take balls and make sure that they come in as it puts them in line. So what we want to prevent with these two brushes is we don't want to prevent two balls from coming in and jamming the system, because in case two balls come in and then they smush together, so we can't really store them now. So this is called serializing, and then have our system. So possible, so we can shoot on a fast succession. And also the hopper also includes a superstructure. So this is a superstructure. It's kind of like this frame that everything else mounts to. So if you see in a top level or like a robot CAD, you can see that the superstructure shooter is mounted to it, and then these climbers mounted to it. So kind of holds everything together. So after CAD designing a model, we sometimes use FEA, which is finite element analysis. So this thing has a tool to create a simulation of where our parts will bend. So if you see, this is our original part, and then after FEA, you can see there's a bend right here. And that's not great, because then we know I'm applying 4 times the robot's weight. So we're applying more weight than we need, but I just want to see where it can possibly bend. So if you look deeper, so right here on the chart, you can see this red arrow right here, and that points to a color. So what that means is that anything below here, like dark blues, means that the material won't bend, and anything above it means that it's bending. So all this green right here will mean that it will bend, and then this blue means it will be fine. So that's how we can kind of predict where our robot will break. So after we CAD, we manufacture the robot. So based off of our 3D model, we make 2D drawings. So I can kind of show you right now. So this is my 3D model of a part. And then after that, I turn it into a 2D drawing, which then, so it makes it easier for manufacturers to create it. So we actually have so in our workshop, we have different tools, different machines, and these machines allow us to create custom parts. So this is a mill. It's kind of like a drill, but it's very accurate. And then we also use a lathe, which is for shafts. So it's kind of like, if I want to create like an axle that holds a wheel, I would use the lathe. And then we have a CNC router. So this is what I can use to create more complicated parts. So CNC means that the computer drives it. So like this plate that has all this like pocketing right here, all these like cool like pocketing shapes, that is what we would put on the CNC router, because it would be able to cut with precision, with the precision of a robot. And then we also have a CNC mill. So this is for smaller parts, but it is extremely accurate. So this thing's accurate up to 1/1000th of an inch. Well, it's accurate to like 1/100th of an inch. So this is an accurate version of a CNC router. And then after that, we have Electron. So this is kind of this looks really confusing, but it's a model of our control system. So what we first have is a 12-volt car battery. So this is, you can actually just take this out of your car if you wanted. And so this power our robot. And then it goes to the PDP, which is the power distribution panel. So off of this, you can power all the motors. So you can see positive. So the red is positive and black is negative. So we have positive and negative running to the motor controllers and then the motors. So this is where the power, this is how we power to the motors. And after that, we also have CAN wire. So this like dashed yellow line is CAN wire. So this CAN wire is essentially signal wire. So this is how we tell our motors and like our entire robot what to do from the programming. So we essentially upload all of our code to the RoboRio, which is it's essentially like your CPU in a computer. So this is the computer that tells everything, your entire robot, what to do. So these are just pictures of our robot. So we build, so this is like the shooter right here, and then we add it onto the main assembly. So we actually built 2 robots. So we built a painted one, and this one's for competition. And then we built a practice robot, which is for just us practicing. Most teams don't do this, but we can afford to do it because we have great sponsors. So so we can program on this and then get practice drivers on this one. And then we also use 3D printing. So 3D printing is additive manufacturing, which means that we add on material to art. So we used a Forged, which is a very fancy printer. So what it does is it prints nylon with chopped fiber. And carbon fibers are really composite that will make very light parts close to the same strength as aluminum. So this makes prints really nice parts. So you can see this is one of our parts. This is a gear right here. And then we also use a Prusa, which is a printer that prints ABS and PLA, which is just plastic. This is a little bit weak. The upside of this is that it's really fast. So if we want a part made in like one day, then we can print on the Prusa instead of the Mark IV, which will take quite a bit to print. So our final product is this robot right here, which is 27 by 30, so 27 by 30 inches, and then it's 27 inches tall. And it has a weight of 125 pounds. So we spent around 8 weeks designing this and building it. So as I mentioned, at the beginning of each match, you have a 15-second autonomous period. So this is pre-programmed code by programmers so it cannot be controlled. Let me show you over here. So yeah, so this was actually really tough for programmers because they had to figure out where the robot was and like use sensors that track the amount of revolution on like our drafts, which means that they had to count how many times the wheels spun around to see where our robot would be on the field. So after that, so in the last 30 seconds, we also have to climb. So our robot was only 20 inches and we needed to reach 75 inches. So this robot started at 28 inches and it needs to reach around its height, 2.5 times its height, starting height. Arms come up like here, and then this is us testing it. So we line up with this drum right here and climb. Wait. There we go. So the gearbox on the timer needs to be able to lift. Need to be able to be 125 pounds. So also another major part was accuracy. So we needed to ensure that we would try to get inside the inner port so we can get the maximum amount of points per ball. So if you see here, this is a slow motion. And you can see that so the last one didn't make it quite in, but that's pretty close. That's pretty good accuracy for me. Yeah, so that's my robot. Unfortunately, due to coronavirus, we weren't able to compete this year. Hopefully next year or like in the off season, maybe when this thing dies down, there will be more competitions for us to attend. So yeah, if you're interested in first, you can email me or I can put you back with my team or the first website where you can sign up for other teams. So thank you.
You're muted, Steve.
Okay, we're looking for questions from the audience. So you can put a question in the text or you can raise your hand. All right, we have commendations. Good job, Alan. Nice job, Alan. Yeah. And here's the first question. It's from Luke Johnson. And the question is, what are common world applications of FIRST Robotics?
So there's not really a real application, but it's kind of like the manufacturing design process that is the application. So like for me example, when I'm designing the robot, I have to I actually use like real industry standard parts and parts to make sure that my things are built. And actually, what we use on our robot, we actually buy from a distributor that distributes to machine shops and other companies that actually are industry.
Yeah, when I look at what you're doing there, Alan, the skills you're gaining are amazing. And it's unfortunate, I think, that most young people never get to do anything. You know, they're stuck in school where you read books and you're actually doing things that are useful. Oh, spoken like a scientist. All right. Okay, here's a good question. How did you hear about FIRST? How did you get started with FIRST?
That's actually, so I started with FLL, which is which is the Lego Minds version of it when around 4th grade. I think I learned about that when, how did I learn about that? I think mom actually was finding some stuff for me when I was 4th grade. And she was like, oh, check out this FLL thing. Because I was really interested in Legos at that time. So I think, yeah, I think it's my mom that introduced me to FIRST. I don't know how she found out about it, but yeah.
Yeah, excellent. It helps to have parents who are looking for enrichment. So how many Southern California teams are there?
I would say there's probably 100. It's
Wow.
quite a bit.
Okay.
Maybe 300. There's a lot of teams.
That's impressive. And each team has, you're suggesting, about 30 people on it?
Yeah, about the people.
Okay.
Some teams have like 60 people.
I see. You can have a big team. Yeah.
Yeah.
So on your team, how many work on CAD and how many work on the electronics? Is it kind of evenly distributed?
Kind of. I think more people on our team are interested in manufacturing because it's cooler. So we have 6 people CAD. We have 5 primers. We have, I think, around 10 people on electronics, and then manufacturing is the rest of them. I don't know how many people on manufacturing, but manufacturing is generally popular because machines are way cooler looking.
Yeah, right. It's fun. It's fun to use the machines and build things. Yeah. So where do you do that? The machining of the parts and all that.
So that's in Irvine. We have a sponsor that lets us use some part of the shop, and we have to get sponsorship to buy the large machines that we use. So, which is nice. So it's in Irvine.
Okay. Yeah. So I've heard that FIRST is expensive. You have an idea how much your yearly budget is?
Well, so each robot costs $5,000. So we have to build 2 of those, which is $10,000 alone on robots. But also other parts, I think between $40,000 to $70,000 is our yearly budget. But we get those all from sponsorship.
Mm-hmm. Okay, here we've got a question from Theo. Is the weight of the robot a big factor? And if it is, what weight-saving strategies do you use?
Yeah, it's a huge factor. So each robot has to be under 125 pounds. So our team, we're notorious for going way over that. So like when we finished, we were probably at like 130, and we have to reduce weight after. So we usually finish around 6 weeks. We finish our comp bot around 6 weeks, and then we spend 2 more weeks. We spend 2 more weeks trying to get our robot below 125 pounds.
I see.
So yeah. So
pare it down. Okay.
So what we do to save weight is, can I share my screen again?
Yes, please.
So what we do to save weight is, you see these like triangles right here? So this is like pocketing. So like in some parts we can reduce the weight by half, like doing this pocketing. So we use triangles because strongest, they have the most amount of sides, so they're the strongest when you apply pressure up, I think. So like, so parts that don't really have that high of that aren't that don't hold the robot together as much, we can pocket. So like this right here, even though this holds the shooter up, the shooter's only bolted on one face of this, so we can pocket the outer side. And also like this climber right here, this is 1/8 inch material, so the wall this is 1/8 of an inch thick. So on this we can pocket it because it's not really holding up, because when the robot goes up, it's up straight up and down. It's not actually side to side. So as long as there's good support on the sides, we can pocket it in the middle.
Excellent. Yeah. Question from Ms. Perkins: how many hours do you spend each week on this project?
It's a very big time commitment for sure. I spent around, I'm gonna say 300 to 400 hours, a 12-week period on this. So divided by 12 is
30 hours.
30 hours a week. Yeah, but most people spend like 15 hours a week, which is still a lot, which is like 8 hours on Saturday and Sunday working on this. So it's a definitely big time commitment.
All right, thanks again, Alan. I'm going to now start the breakout rooms. So we have 23 participants. I will start with 4 rooms, and okay, so you'll be in a breakout room soon. 1 will be mine, 2 will be Mr. Myers. So let's put him in first, and all his students. One more. Okay, let's go to room 3. Actually, let me do room 1, which is mine. Boom, 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 boom. Okay, room 3 will be Holtz. Doot, doot, doot. Doot, doot, doot. Doot, doot, doot. Doot, doot, doot. Okay, I'm going to put Mrs. Perkins in my room. And there we go. Okay, I'm opening the rooms. You'll be with your small group. I get to watch the green dots. Boom, boom, boom. All right, here we are. So I'll ask you to give some feedback aloud if you can to, this is the first time we've tried something like this where a student is able to present something interesting that they're doing. So Anna, your thoughts on, should we try to do something like this in the future?
Yeah, I think it's really cool. I mean, I liked how Alan was presenting it, and it sounded really interesting.
Great. How about you, Joey?
Oh, what? Sorry.
I'm asking you to make a suggestion whether you think we should try to invite other students to share their interesting experiences as Alan did today.
Yeah, I think we should like hear their ideas, like their different views. Like it seems cool.
Okay, how about you, Taro? Taro's mic is going in and out. Mute, unmute. All right, we're not able to hear you, Taro, but maybe in a little bit we will. Odin, what are your thoughts?
So I'm eating food, but I think it's pretty cool.
You're eating food, that's fine.
Yeah. Yeah, like the design process is really cool, I guess, and all that. Like how they plan it out over like on CAD and all, and they use all these programs like to cut weight and see like where the weight is distributed and like how much it can handle. So I think that's like really cool and all that. So
Yeah, it's a great way to learn engineering. And
yeah.
we should try to get more of that into our school.
Yeah, more engineering type of stuff. Yeah, I think that'd be it.
Yeah, different ways of learning. You know, school is okay, but you can learn so much more out of school. And some people don't realize that. Some people think, oh, school is so important. I've got to do my schoolwork, and that's all I do is school. And it's not. It's limiting. It's limiting. There's a lot more too. There are experiences that can give you a much better education than just school. All right, Tara, we got your message that your internet is not so great right now. But Mrs. Perkins will be monitoring the chat there. So with that in mind.
We do have, it says, I like how we get to hear students with their different unique viewpoints. That's what Taro said.
Okay, great. Yeah, you've been a really good participant, Taro, in the text chat. I got to see the transcript from yesterday and the day before, and then Taro's given good feedback via the text. So thank you for that. Thank you for that participation. So that begs the question of you know, we got a small group here, but do you as individuals have topics or experiences that you think other students would like to hear about? So I won't put you on the spot today and say, what would you talk about? But I do want you to consider it. Alan, I learned about what Alan was doing maybe a couple months ago because he had to get a permission slip to go to the competition. And so that's when I learned, oh, you're doing FIRST Robotics. And so he had to go to San Diego for that, for the regional competition, I guess. And unfortunately, it got canceled. But so that's how I learned. Otherwise, I would be ignorant of his participation. So it may sometimes, you know, some people are shy and they're not likely to put themselves out there and say, oh, I am doing something interesting, but I want you to consider it because I think it's a great thing to share. And how would you know if we didn't have this opportunity for sharing? How would you know that people are doing these amazing things? All right, I am going to open up. Do you have any questions for me today? Usually the answer is silence as we're going. Okay, so one thing I want to know from you all is whether you're feeling dragged down by the COVID-19, and is it dragging you down? Are you seeing hope for the future, or is it just kind of, it's flat? I'm not being dragged down, I'm just flat. So I'm hoping each of you can tell me something about how you're feeling. We'll start with you, Alan. How are you feeling?
I'm feeling all right about the COVID-19 pandemic. There's like a lot going outside, and I can't go outside, but like at home, I think schoolwork is like how it was. There's just more homework instead of classwork, and yeah, it's just the major difference for me personally is that I just can't go outside and I can sleep in later.
Okay, well, sleeping in is good.
Yeah.
So you're thinking it's about the same amount of work that you had before. So that's not debilitating. And are you finding the work has the same kind of reward of saying, yes, I've done my work, I feel good about it. How do you feel about that?
I think it does have kind of the same reward, because after I finish it and I see like, oh, I got a good grade in the grade, then I'm like, then
Okay.
I feel great about the work.
Yeah, all right, excellent. How about you, Joey?
Hopefully I find it's gonna like be over soon. Like we can go out like sooner. Cause honestly, just being cooped up here just like kind of brings me down a bit.
Mm-hmm.
But I still notice people like go outside, and I feel like the more people go outside, like the longer we're just gonna like be in. So hopefully we just
Yeah, the idea of those who take their liberties too soon are going to make it harder for all the rest of us who are following the rules. Yeah, I saw people playing basketball in the park. Maybe it was yesterday. It's hard to know. The days blur. But I thought, yeah, you shouldn't be doing that.
yeah, like a few people at the beach too. So
I see. Anna, what are your thoughts?
It's kind of brought me down because I can't really see like friends, and but I have been learning other things like baking and cooking, and yeah.
Okay, well, that's good. Yeah. Do you see friends like electronically, kind of like we're doing now, or is it you really don't?
Yeah, I FaceTime them, and we do like little mini Zoom meetings and everything.
Okay, great.
Yeah.
Yeah, my son who's home from MIT is he gets together with his friends and he does some kind of game. So they're playing a game and they're talking to each other through Discord, and so, but for him, really, it's like my year. This was a senior year, and it's supposed to be celebration of everything I've accomplished. Instead, it's well, everything's canceled. I'm doing my classes, but they don't really feel meaningful as they're supposed to. So,
Yeah.
all right, Odin, what are your thoughts?
I don't know. It's kind of it's pretty boring now. But like I do like talk to my friends and like play video games with them.
Mm-hmm.
And like school, it's like kind of weird. And like what some people are saying is like next year the schools are like planning on like almost going like college, where like you only have like certain days it's only like certain like kids. Like maybe one day it's like 10th graders, and like half that day it's like one class and all that. That's gonna kind of be like a really big change. And yeah.
Yeah, a lot of uncertainty for what the future holds. Yeah.
Yeah.
Okay. Taro, if you're able to speak, we'd like to hear you, and if not, we understand.
I'm just like not sure what to do right now. Just
Okay.
speaking.
Taro said something in the chat. Taro says, I feel okay about the whole thing. I miss going outside, but the sleep is nice. Yeah, okay. Workload seems like a lot, but it's an illusion because we don't have an official schedule. Yeah, okay.
That's true.
Yeah, for me, it seems like my day goes, and I think, well, I don't feel like I did 6 hours of work, so where did the time go?
Yeah.
Where did it go?
Yeah, it feels the same for me.
Yeah. So it's weird, this time dilation or contraction. I don't know which it is.
Yeah.
All right, well, thank you for your thoughts. And as I said, consider whether you have things to share with other students, as Alan did today. Thanks again to you, Alan. That's very inspirational. And I'm going to visit the other breakout rooms. And if I'll hope to see you tomorrow. I'll hope to see you tomorrow.
Yeah, for sure.
Bye-bye.
Thank you.
Thank you.
Bye, everyone.
Bye. Thank you.
Bye.